everyone. In this video, I will be discussing about virtual memory management. But before that, let's talk a little about what is a virtual memory. A virtual memory is a memory management capability of an operating system that uses hardware and software to allow a computer to compensate for physical memory shortages by temporarily transferring data from random access memory to disk storage. Virtual address space is increased using active memory in RAM and inactive memory in hard disk drives to form contiguous addresses that hold both the application and its data. To better understand that, let's take a look on this picture. The green box, which is our RAM, is already full, but the program tree on the left blue box is requesting to be processed. So program 0, which is the first program that has been processed, will be mapped to the disk. And now the program 0 is on the disk, and there is a free space on the RAM where program 3 can take in. That is a virtual memory. Now let's talk about its memory management. The first one is the demand paging. What is demand paging? The basic idea behind demand paging is that when a process is swapped in, its pages are not swapped in all at once. Rather, they are swapped in only when the process needs them or on demand, which is termed as lazy swapper, although a pager is a more accurate term. If we take a look on the picture, the box on the left, which is our main memory, swap out the program A to the disk to temporarily store the program so that our main memory has more space than the program B, which is the demand program that can be found on the disk, swap in into the memory. So program B can now be processed faster because the main memory has now more space. That is demand paging. The second memory management is the page replacement. A page replacement is as studied in demand paging. Only certain pages of a process are loaded initially into the memory. This allows us to get more number of processes into the memory at the same time. But when a process requests for more pages and no free memory is available to bring them in. Following steps can be taken to deal with this problem. One is that put the process in the wait queue until any other processes finishes into execution, thereby freeing frames. 2. Remove some other processes completely from the memory to free frames. 3. Or find some pages that are not being used right now, move them to the disk to get free frames. This technique is called page replacement, which is most commonly used. We have great algorithms to carry on page replacement efficiently. So, what page replacement means is that when the main memory is already full and there are still programs or pages that are requesting to be processed, then that means the program or pages in the main memory will move out and put it on the disk so that the requesting program or page will now have some space in the memory. There are different page replacement algorithms for this, and I will be discussing two of them. The first algorithm is the FIFO page replacement. It is a very simple way of page replacement. It is a first in, first out. As new pages are requested and are swapped in, they are added to tail of a queue, and the page which is the head becomes the victim. It's not an effective way of page replacement but can be used for small systems. To better understand it, let me show you a short demonstration. This is our these are the processes or the pages. Then this is the page frame that can be found in the memory. The page table is the data structure used by a virtual memory system in a computer operating system to store the mapping between virtual addresses and physical addresses. So the first process is the page 1. Since the table is empty, then then we will put it, and since 1 is not on the table, which means it has page fault. A page fault is a type of exception raised by computer hardware when a running program accesses a memory page that is not currently mapped by the memory management unit into the virtual address space of a process. Then the next process is 2. So let's just copy that 1 and put the 2 since 2 is cannot be found on the table, then it has page fault. The next is 3, and again let's just paste it and put the 3. Since 3 is not in the table, then page fault occurs. Then the next is 4, which is not found in the table, then page fault occurs. The next one is the page 1, which is already on the table, so let's just copy that 2, 3, and 4. Then there it will be a page hit. A page hit is an opposite of page fault. It is when the process or the requesting process is already on the page frame. So next process is the 2, which is already on the table, so just copy it, 3 and 4. Then a page hit occurs. So the next one is the page 5. We know that the page frame is already full, so we will implement the first in, first out. If we take a look at the very first column, page 1 is the first page that came in. So page 1 will be replaced with page 5. So since 5 is not found on the table, then page fault occurs. The next is 1. Since if we'll take a look at that column, 2 is the next page that came in. So 2 will be replaced with page 1. So fault occurs. The next one is 2. If we take a look at the column, page 3 is the next that came first. So page 3 will be removed, then replaced with page 2. Then fault occurs. And the lastly is the page 3. If we look at that column, page 4 is the next page that came in. So page 4 will be replaced with page 3, then a page fault occurs. In this algorithm, there are at least 8 page fault occurs. So this is the FIFO page replacement. The second algorithm is the least recently used page replacement. It is a greedy algorithm where the page to be replaced is least recently used. The idea is based on locality of reference. To better understand this algorithm, let me show you a short demonstration. Still, we will use the same processes or pages. The first page that needs to be processed is the page 1. So page 1 is not on the table, so it means a page fault occurs. The next is the page 2, then a page fault occurs. And the next is page 3, then a page fault occurs. And the page 4 is not on the table, it means it's a page fault. And again, page 1 is already on the table, so which means it is a page hit. And the page 2 that is already on the table, which means it is a page hit. Now that our table is already full and a page 5 is requesting, so we need to replace some here. So if we will look at here, we will know that page 2 is the most recently used, next is 1, next is 4, which means 3 is the least recently used. So we will replace the 3 with page 5 and a page fault occurs. The next one is the page 1, which is already on the table, so we just copy it and a page hit occurs. Then the next requesting is the page 2, which is already on the table, which means a page hit occurs. And lastly, the page 3. If we will compare the 4 pages, the 1, the 2, the 5, and the 4, we will know that 2 is the most recently used, next is 1, and next is 5, which means page 4 is the least recently used, which means we will replace the page 4 with page 3. Since page 3 is not on the table, then a page fault occurs. As you can see on this algorithm, there is a less page fault which has only 6 page fault compared to first in, first out page replacement which has 8 page faults. So that's all for these algorithms, and let's proceed to our last memory management, which is the thrashing. So the last memory management is the thrashing. It is a process that is spending more time paging than executing is said to be thrashing. In other words, it means that the process doesn't have enough frames to hold all the pages for its execution, so it is swapping pages in and out very frequently to keep executing. Sometimes the pages which is required in the near future will be swapped out. In the in the previous discussion, we talked about the space limitation of the physical memory. If there are still processes or pages that needs to be processed, some of the pages in the physical memory will be swapped out to the disk, but virtual memory is also physically limited by the available disk space, and the disk space is restricted by the computer architecture. So when both memory are full, then thrashing will occur. Some programs will stop responding or the computer freezes. Thrashing or disk thrashing describes when a hard drive is being overworked by moving information between the system memory and the virtual memory excessively. Thrashing occurs when the system does not have enough memory, the system swap file is not properly configured, too much is running at the same time, or has low system resources. When thrashing occurs, you will notice the computer hard drive always working and a decrease in system performance. Thrashing is serious because of the amount of work the hard drive to do, and if left unfixed, can cause an early hard drive failure. To resolve hard drive thrashing, you need to either increase the amount of RAM in the computer or writing programs that uses memory more efficiently or decrease the number of programs being run on the computer. So that is thrashing. So that's all for this video. Thank you for watching and I hope you understand even a little thing on this video.